Okay friends, very good evening. Today we are going to discuss about short noise. This short noise is also known as Schottky noise. It was first demonstrated and proposed by Schottky in 1980. The fundamental basis is the granular nature of the electronic charge. The two conditions must be satisfied for short noise to occur. There must be a direct current flow and there must also be a potential barrier over which the charge carriers over which the charge carriers hub. The ordinary linear resistors do not generate short noise despite the quantized nature of electronic charge. The short noise current to depend on the charge of the electron DC current flow and the bandwidth. The short noise current is given by I and I square n is equal to 2q into IDC into delta F, where IN is the RMS noise current, Q is the electronic charge, IDC is the DC current in amperes. Delta F is the noise bandwidth in hertz. So the short This is very mysterious noise. No source of mechanism is identified for this. Its spectral density decreases with increase of frequency. So it is called 1 by F noise. So it is called 1 by F noise. It is often called excess noise since this noise is in addition to what is expected from thermal noise considerations. It is found that a resistor exhibits 1 by F noise only when there is DC current flowing through it. Metal, film and wire wound resistors exhibit the smallest amounts of excess noise. Smallest amounts of excess noise. Flicker noise. It is not having specific mechanism, so it can be modeled as n square is equal to k by f power n into delta f, where k is empirical constant, n is exponent, its value is close to unity or equal to unity, m is RMS noise. So integrate the density to find the total noise in a frequency band bounded by a lower frequency f1 and an upper frequency fh. N square is equal to f1 to fl to fh. K by f df is equal to k into integral of fh by f1. This equation tells us that the total mean square noise depends on the log of the frequency ratio rather than simply on the frequency differences, as in thermal and short noise. So, flicker noise in resistors. So, what is flicker noise in resistors? The flicker noise also shows up in ordinary resistors where it is often called excess noise. It is found that a resistor exhibits 1 by F noise only when there is DC current flowing through it and the noise increasing with the current. The flicker noise in resistance is given by En square is equal to K by F of R square by A into V square into delta F. In this K value is roughly 5 into 10 to the power of minus 28 S2 of M square, S2 to M2. R is sheet resistivity, A is area and V is voltage across resistor. In electronic device, 1 by F noise arises from a number of different mechanisms and is most prominent in devices that are sensitive to surface phenomena. Hence, MOSFETs exhibit significantly more 1 by F noise. This 1 by F noise is due to charge trapping phenomena. That is some types of defects and impurities can randomly release charge. This leads to 1 by F noise in MOSFET and BJT. So MOSFET or surface devices, so they exhibit flicker noise. Larger MOSFETs exhibit low flicker noise because they have larger gate capacitance reduces the charge fluctuations. The mean square noise current is given by I square n is equal to k by f. Gm square WL C square Ox into delta f is approximately equal to k by f into WT square A into delta f. Where A is area, A is equal to WL and K is a device specific constant. Flicker noise in junctions. Forward biased junctions also exhibit 1 by F noise. The noise is proportional to the base bias current and inversely proportional to the junction area, where the constant K typically has a value of around 10 to 25 A into meter square. So, this is what the flicker noise in MOSFET. Noise factor and noise temperature. So, what is noise factor and noise temperature? A useful measure of the noise performance of a system is the noise factor. It is defined as F is equal to total output noise power by output noise due to input source. It is a measure of degradation in SNR that the system introduces degradation larger than the noise factor. If system does not introduce any noise, that is, the output noise is due to external only, then noise factor is unity. If noise factor is defined in dB, it is called noise figure. Noise temperature Tn is defined as the rising temperature required of the source resistance for it to account for all of output noise at reference temperature. It is related to noise factor as F is equal to 1 plus Tn by T reference is equal to Tn is equal to T reference into F minus 1. Noise factor and noise temperature. Noisy two-port driven by noise equivalent noise model. So these are the two-port driven by noise. Noise factor and noise temperature. A calculation based directly on equation requires the computation of the total power due to all of the sources. An equivalent method is to compute the total short circuit mean square noise current and then divide the total by the short circuit mean square noise current due to the input source. The expression for noise figure becomes F is equal to Is square plus In plus Ys En whole square divided by Is square. In order to get correlations between En and In expressed as the sum of two components. IC is correlated with enable may be treated as proportional to it through a constant. IC is equal to YC into En. The constant YC is also known as correlation admittance. Correlation admittance. From the above figure, from the above three equations, the noise factor becomes F is equal to I square plus Ig plus Yc plus Yn into e power n mod of square by In square is equal to 1 plus In square plus Yc plus En square by I square. The above equation contains three independent noise sources. Each of may be treated as thermal noise produced by an equivalent resistance or conductance given by the equations, that is Rn is equal to En square 4 kT delta F. Gn is equal to In square by 4 kT into delta F. Gs is equal to Is square by 4 kT delta F. The noise factor and noise temperature. The expression for noise factor can be written purely in terms of impedance and admittances is F is equal to 1 plus Gn plus Yc plus Ys mod of square into Rn is equal to 1 plus Gn plus box of Gc plus Gs whole square plus Bc plus Bs whole square into Rn by Gs. By solving above equation, the optimum values and the noise factor is minimized according. So Bs is equal to minus Bc is equal to B opt. Gs is equal to square root of Gn by Rn plus Gs. Gc square is equal to G opt. Noise factor in terms of F min and the source admittance, F is equal to F in F minimum plus Rn by Gs into Gs minus G opt whole square plus Bs minus B opt whole square.